All right, we'll go ahead and get started. Might see some more people trickling in, but the first few minutes will be review. So go ahead and get started with that. Welcome back, everybody, to part 3 of this series of workshops on getting going with R. And I like this series of workshops because as it gets further along, it gets more interesting. So I suspect most people attended 1 or 2 of the previous workshops, but for anyone who's new, welcome. I'm Andy Lyons, and I am with the Informatics and GIS statewide program within UCANR, and pleased to be the instructor for this workshop series. And I'm assisted on the back end here with 2 of my colleagues, Ben Satzman and Genoa Stars. So thank you to them for helping us out, and we'll just go ahead and get going. I won't do an intro of myself or our group or the workshop series, but if this is the first time for anybody here in part 1, if you go to the slide deck for part 1, there's some background there. And as always, happy to meet with people outside of these workshop series if you have questions about our unit or anything that we're covering in the workshop series. So without further ado, let's jump into part 3 of the workshop series. We will start off with a little bit of a review, and I will pause to see if there's questions from any of the content from last time. I should give a shout out here that I was remiss in not sending out the homework assignment for the last week's workshop, part 2. But that will be on the website shortly. Let's see, I just pushed it up. It'll come up here in a second now. All right. But let's begin with a review of what we covered last time. So this is what we're going to do today. We'll start out with a review, and then we're going to jump into data wrangling, which is where we're really getting into more of the power and I think the fun of using R to work with data. Okay. So let's talk a little bit about what we covered in last time. So last time we looked at base R. Today we're moving into working with some packages from the tidyverse, which are really well equipped to work with data. But last time we looked at base R, and we saw some of the basic plotting functions that you can use to make kind of exploratory plots of your data, histograms, box plots, and if you have two data sets, X and Y, for example, you can do scatter plots, line plots, and so forth. Okay. And next week, we will see a package that's designed specifically for plotting and specifically for enhancing the kinds of plots you can do with R, and that's ggplot2. So stay tuned for more plotting next week. Last week, you might remember, we also talked about packages. There's thousands and thousands of these. They've been developed by our users. Many of them are academics. And what they mostly provide you are additional functions, sometimes data sets to use with those functions, sometimes data sets are the primary purpose of the package. And these packages enhance the functionality of R, often for specific domains, specific types of method of analyses, specific types of data, for example, genomics or spatial data. So packages are really one of the strengths of the R ecosystem. The tidyverse is a family of packages that have been, they're newish, maybe 10 years roughly for many of these packages. But they're well developed, they're well supported, they're well designed by professional data scientists. And we're going to be working with some of these today, tidyverse family packages. Before you can use a package in R, you have to install it. That just basically means downloading it and unzipping it onto your hard drive. You can do that in RStudio quite easily. There's a little button called Install Packages. You can click it and then type in the name of the package. You do need to know the name of the package. And then you can also install packages with the command, the Install Packages command. All right, so we talked a little bit about packages last week. Before you can actually use the functions from a package, you need to load it into memory with the library function. which is often what you do first when you start a new R session. We also talked about functions. Getting good with functions is also part of the getting good with R. You need to know the name of the function. And sometimes that means you need to know the package where it's coming from. So that's half the battle, because all functions have help pages that can help you understand how to use that function once you figure out what it is. All functions have arguments that you put inside the parentheses. You need to know which of those are required. And it's helpful to know what order are they expected and which of them are optional, right? That can help you write commands that won't give you error messages because you skipped the required argument or you didn't put them in the right order. You need to know, what does it return? Does it return a number? Does it return some sort of statistical model? Does it return a spatial object or something else that's not, specific to a kind of data or a kind of analysis? All functions return something. And a few functions also take actions such as draw plots, importing data, writing data to disk, and so on and so forth. Right? So those are the 4 things. If you know about those 4 things, then you can put that function to use. We also looked last time about piping syntax. This is a way of typing in or chaining together a number of functions without the traditional nested parentheses. And piping works using these pipe operators. This is the newer version of them. It's 2 characters back to back. And when you pipe functions, or when you chain functions together with these pipes, basically R will evaluate each item in turn and then feed the results of one argument into the next function as the first argument, which you can omit when writing the functions. So we'll see some more examples of that today. Piping is really handy when we're working with data wrangling. Coming to data, we talked about the most common data class for tabular data in R is the data frame. Today, we will learn that data frames are often called tibbles. Data frames and tibbles are basically equivalent. You can explore what's in a data frame with the head function. That will show you the first few rows of it. You can open it up in its own pane in RStudio with the view function. That's a capital V. You can grab an individual column with the $sign operator. Those are all kind of functions from base R. Today, we'll look at more functions for working with data frames from the tidyverse, from dplyr. We looked at how to import data. Read.csv, it's a venerable function from base R. You can use it to import CSV files. There are many flavors of CSV files, and this function has many arguments that you can use to specify the structure of a CSV file. For example, does the first row contain the column labels or not? And so on and so forth. If that's painful, and it often is, you can also turn to the Import Dataset button within RStudio that opens up a graphical wizard that allows you to select a file, get a preview of it, and then say, are the columns separated by commas or tabs? Are they delimited or not? And so on and so forth. There's also a bunch of packages that you can use for importing specific file types, such as SAS or SPSS, or if you have your data in a database like SQLite or something like that. There's lots of packages like that. Pretty much whenever you're importing data, you have to provide a path to the data file or the URL. Path names for the local file, they can be absolute, starting with the drive letter and going from there, or relative. And when we say relative, that means relative to the working directory, where the first character in the path is usually a dot representing that working directory. If you are working with R to analyze data in a project that you might want to reproduce, you might want to put aside and come back to many months from now, you might want to share it with colleagues or move it around, a very good practice is to use RStudio projects. So this is what many, many data scientists do. Basically, you create a folder for your project. Inside that folder, you have subfolders, maybe one for the data, maybe one for your outputs, and then a script or scripts to do the different steps of your project. And then if you create an RStudio project inside that folder, then every time you open up that RStudio project in RStudio, the working directory is set to the project folder, and then you can just use relative path names and everything works pretty well from there, right? So this might be overkill if you're just doing a quick and dirty R script to clean up some data. But if it is a project that you'll want to work with repeatedly, this is a good practice and good habits to get into. All right. And then finally, I'm a big advocate of cheat sheets. There's a couple cheat sheets in our workshop. I believe they got some. I don't have links to these cheat sheets here, but there's a couple links here. I'll put these in the chat window again. I'm a big fan of cheat sheets as a way to help people learn what functions are commonly used. Here's one. These are just a couple. There's many good cheat sheets out there. R for Ecology. This is a cheat sheet from a instructor. This instructor does charge for his courses, but his cheat sheets are free. So check those out. So let's talk about data wrangling. A lot of us hear this term quite a bit, and it is important. So let me introduce it. I don't know if there probably is a textbook definition out there, but the definition I use when I'm thinking about data wrangling, it's whatever you need to do to get your data ready for what you're trying to do, which might be analysis, might be exporting it so you can use it for something else, might be visualization, but it's all the stuff you have to do. You might be lucky. Maybe you're given a CSV file that's really well structured and has clean columns, clean labels, no missing data. But in the real world, you might get a spreadsheet where every tab represents a different plot, a different year. You might get lots of spreadsheets from different plots, different years, different field text. I've had projects where I've gotten like literally thousands of little tiny files, all contain data, little tiny slices of data that have to be put together, right? So there's lots of, and this is often the pain point, and it's often takes an enormous amount of time that would be better spent doing the analysis or the visualization. So when I think of data wrangling, which is also referred to as data munging, data manipulations, data transformations, these are some terms I've heard. It's going to be one or more of these kinds of operations. And again, we're talking tabular data here, or I'm referring to tabular data in this specifically right now. But you may have to drop columns. You may have columns which just have awful names and you can't, you don't want to use those names. Google Forms and other kind of survey tools are the worst because often the column name is the question. The columns might be out of order. There might be a lot of columns you don't need. Oftentimes you need to create a new column based on some kind of expression. Rarely do you need all of the rows. You might need to sort the rows. Your data might have like thousands and thousands of records, but really a lot of there's repetition and you just want them to be wide, or it could have dozens and dozens of columns. Half of them are empty and you want to go from wide to long formats. That's pretty common. You might find a lot of times columns will be like a acronym or a number that refers to something else that's saved in another table. And you have to join tables together based on a common frame. You might get lots of tables and you've got to merge them together. You might have one ginormous table that you want to split it apart into multiple tables, and so on and so forth. You may need to do your analysis. You may need to do some aggregation of the rows and group them. And then for every group, we do something with those groups of rows. All right. So data wrangling covers all of this and maybe some other stuff, but this is the main thing. So to think about how to get there and what we're trying to get to when we are preparing data for working in R for statistical modeling or something else, it's helpful to think about a tidy data format, because many of the R packages that run statistical tests, that do plots, like to have data that is in this tidy format. So what is tidy format? What does it mean? So it's not a format like CSV versus Excel. It refers to how the data are structured. And in general, a tidy data is where every variable is saved in a column, its own column. Every observation is saved in the row. And again, that observation, here we're using the word observation. It could be a case, it could be a spatial feature, it could be a measurement or a time period, but however you define observation for your analysis. And then each type of observation is stored in a single table. Okay? So in general, these are the adjectives or the properties of a data set that would make it a tidy data set. So let's look at some examples here. So in our first example here, we have, it's called storms. This is a data frame that comes built into R. It might be part of the dplyr package. So once you load the dplyr package, I think you can then look at the storms data frame. So my question to you is this storms table, is this tidy? Would you consider this to be tidy? Every row here, just as the background, represents a storm, a hurricane, I believe in the Atlantic, at a specific date. So anybody put your thumb up if you think this storms table looks tidy to you. Is every variable saved in a column? Does every row represent an observation? And does the table contain the same type of observation? All right, I see some thumbs up. Anybody else have an opinion? Yeah, I would say yes, right? Every row represents a storm at a specific date, right? So you might see multiple rows for the same storm, but we're defining the row as the storm on that date. So that's a well-defined observation. And yeah, we have a column for wind, a column for the pressure. Those are the characteristics and the storm name. How about the next one? Cases. This is not uncommon to get data where you have multiple columns for different time points. Is the cases table tidy? And if not, why not? What do y'all think? Anybody want to unmute and share an opinion on this one? Danielle, I would agree that I would say no, this table is not tidy because, well, let's first of all think about what are the observations here? What are we trying to record here? Case, we don't know the background of this table, but it's like the number of cases of something. I don't know, pneumonia or lost dogs or something or other, but it's case, it's clearly cases. So the number of cases should be in one column, right? We said, one of the properties of tidy data sets is that every variable, such as the number of cases, is in a single column. And here it's spread out across 3 columns. So the way we would make this tidy, we would go from this wide format into a long format where we would have a column for the country, a column for the year, and then a column for the number of cases, right? And that's not hard to do with R. And we're going to see how to do that by the end of today. And how about the final table shown here, the pollution table? Does this look tidy to you? Anybody want to give a thumbs up, thumbs down, put something in the comments chat? I would say yes, right? You might think, well, we have duplicate values here. You know, New York appears twice, London appears twice, but clearly this is a measure of the amount of pollution, but two types of pollution or two types of particles. So the particle size, that's a property of the count, right? So every row represents the measurement of pollution particles, and part of the properties of those measurements are the size of the properties. So this would be ready to go. And even if you're only interested in the large particles or the small particles, or you don't care about differentiating those, that's easy peasy to do in R, to group those together, to treat them separately, and so on and so forth. So that's a tidy table. Sometimes it's a little shades of gray, but so that's often what we're trying to get to, right? So whatever your data comes in as, that's what we're often trying to get to work efficiently at the analysis stage and at the data visualization stage. So some of the pain in working with data can be solved when you import it, right? You don't have to import and then start cleaning up your data frame. If you use one of these packages, which are kind of like specialized importing data packages, readr can import all kinds of data in text files, CSV and the many flavors, .txt. readxl has lots and lots of power for importing Excel files. Google Sheets 4 is something I use quite a bit just because talking about collaboration, it's Google Sheets and Google Docs in general are designed for collaboration, and they work pretty well for that. And you can work with those data in R. We're not going to do a deep dive into using these packages. It kind of takes a little while, but in general, these packages allow you to import tables from different formats, tabular data. They have optional arguments that allow you to do things such as skip rows, which is often something you might find. There are arguments that can tell you whether that file contains a header, such as the names of the columns. You can rename the columns when you import them if the names aren't nice. And you can specify the data type for each column, because particularly with text data, the data type of each column is generally not represented in the text file itself. So here's an example from the readxl package. That readxl package has a function called readxlsx. And here you can see, you would expect there'd be an argument for the Excel file, but in addition to that, there's all these optional arguments. You can specify which sheet. You can tell it to skip the first 3 lines because they contain some other stuff. You can tell it what columns to import. You can also have it rename those columns. And then Excel files will often, Excel does not record the data type of a cell. Files or functions that import Excel data guess that this is a text column, that this is a date column, based on the formatting, or they use other ways to guess the data types. But this package has another argument, an optional argument that you can tell it that, column 1 is going to be text. Column 2, those are actually dates, and so on and so forth. All of these packages have good cheat sheets, so check those out if you want to try that, right? And we'll see an example of importing some messy data in our first exercise. So importing data, you can solve some of your problem there. But once the data are in R, and now you have a data frame or a tibble, then you can start working it with dplyr. Is a good package that can do probably like 85% of the stuff that you'll have to do with data frames. It also has a cheat sheet. This cheat sheet is worth looking at. You'll quickly figure out the most common functions, but there's lots of other functions that you can use within dplyr. So it's worth looking at this. Speaking of common functions from dplyr, these are the ones I think most people use most often. If you do need to subset rows, there's the filter and slice functions. We'll talk about the differences between those. Ordering rows, that can be done with the arrange function. If you do need to only work with some of the columns, you can use the select function. If you only need to work with a single column, you can use the pull function. That's the counterpart to the $ operator. Adding new columns is easy with the mutate function. And then joining, there's a number of functions you can use to join data frames based on a common column. All right. A couple common features about all of these functions from dplyr. All of them take a tibble and return a tibble, right? So the first argument is going to be a tibble, and again, tibble and data frames are the same. This makes them pipe friendly, right? So because they return a tibble, you can pipe that into the next function that expects a tibble as the first argument. And you often see dplyr functions chained together this way. Okay. And all of these dplyr functions, I should say, they take a tibble. They also work fine on data frames. They will convert the data frame to a tibble on the fly. All right, let's look at an example of using some of those functions we just looked at. Again, we'll work at the storms table data frame. Or sorry, storms is a tibble. And these are the columns in it, right? So these are all of the columns here. Right, so, and again, every row represents the strength of a storm on a specific day and a specific hour. You might notice there's an hour column here too, right? So these are the airplanes that fly over the hurricanes, and they measure the wind speed and how big they are and that kind of stuff from the 1970s. So suppose we were interested in pulling out just the storms that were category 3 hurricanes or stronger, because they do have smaller hurricanes and they do have tropical storms in there as well. So here is a expression from using dplyr functions that does exactly that. We start with this storms tibble. We pipe that into the select function, which you might remember pulls out only specific columns because we don't need 10 columns for this purpose. We're just looking for 3. And then we pipe those 4 columns, or the tibble with those 4 columns, into the filter function. And the argument for the filter expression is a category is greater than or equal to 3. Because you might have noticed there's a column called category, and it's a numeric column. And with that one expression, now we have a tibble with only the category 3 storms. Again, that's there might be some. Here's a double record, and that's because there are 2. Because again, there's multiple observations per every 6 hours. All right, so we would probably have to clean this up a little bit more. But that's an example of using select and filter together. Okay, we'll see more examples of that. Okay, there is one gotcha when using dplyr specifically, and that is those functions that we just looked at: select, arrange, sort, or not sort, select, arrange, and others are pretty generic. And there are other packages out there that also have a function called select or filter. So when you type in the select function, when you type that in, R has to figure out, should I use it from the dplyr package, or I also found it in some other package. So this is called function name clashes or duplicate function names. It's not super common, but in general, it does happen. And if you don't specify what package to use, R will just look and see whatever package was loaded first, it's going to use the function from that package. So, which may or may not be a problem, but it's better if you can specify which package you mean. There's 2 ways you can do that. If you use the double colon if you specify the name of the package and then double colon, that you're telling R to use the over function in this case from that package specifically. So that's a good practice, and you'll see this in code a lot, that somebody has entered the name of the package, double colon, and then the name of a function, because they want to either they're reminding themselves or they're being very explicit to R where that function comes from. Okay, so this is actually good syntax. A benefit if you do this syntax is you don't actually have to load the package with the library function. Another technique is that you can use the conflicted package and tell R in advance what package you want it to use if it finds the filter function, if it finds the count function or the select function, and so forth. And we'll be doing this a lot in our notebooks today, because you just specify these function preferences or package preferences, and then you don't have to worry about it after that. All right, so that's how we deal with name conflicts. Okay, it's time for our first notebook. And this is kind of exciting. So in part 1 of our workshop series, we did live coding. You typed in manually. In part 2, we had a couple .r scripts. So working in the script window. And our notebooks are kind of like scripts, but they're a little bit like scripts on steroids. Because, and this is what it's going to look like here. But before we jump into Posit Cloud, I want to kind of show you a little bit about the bells and whistles of our notebooks. So they are text files. So in that way, they're similar to .r files. If you look at the extension is .rmd, that's not required, but that's pretty standard. The first few lines of a R Markdown file, and this is a kind of R Markdown file, are called the YAML header. Just leave that alone. Don't mess with it. That tells RStudio what type of Markdown file this is. The notebook itself contains R code as well as plain text or descriptive text. And the plain text or descriptive text, you can mark it up with these Markdown formatting characters. So for example, the hash or pound sign, when we run this and save the results as HTML, that's going to look as like a heading. And it's going to look like a nice little heading. And that is one of the reasons we're using notebooks, is because you can, after you've run all the code, you can save it as HTML and then keep that HTML file as part of your library in case you ever need to come back to it. So you can use Markdown formatting in the plain text parts of your document. The R code itself is in these little gray boxes, which are called code chunks. And you can insert a new code chunk. There's a command in the menu, you can do it. You can also just manually type in some of these backticks and then and curly braces and then close it with other backticks. They're just part of the text. But when R sees that, it knows that chunk contains R code. So in those code chunks, you need valid R commands or comments. Okay. You can run a command in a code chunk by clicking in that line and then clicking that little run button. Or you can also do, there's a keyboard shortcut for Control Enter that will also run the current line. Something that's different than our script is that if this code chunk produces output, instead of showing the output down in the console or in the plot window in RStudio, it'll display the output of the code chunk directly below the code chunk inline. That's the default behavior. So that's a little unsettling to people who work at the console or scripts a lot, but you can get used to it. And you can change it too if you want it to go back to the console and plot window. If you want to run all of the lines in a code chunk, there's a little green button here that'll run them all together. If you want to run all of the code chunks above the current one, there's a little button that will do that. So sometimes if you forget to run some code above and you're getting error messages like, oh, that object doesn't exist because you didn't run the code chunk that created that object, you can use that little button there. But the benefit comes when you're all done and you click the save button, you save your file, and it generates a HTML file on the fly. And you can also preview that HTML file by clicking the preview button. So we'll see that. All right, so that's in our notebook. So before we start the next bit, here we have, we're going to work with the Palmer penguins data set, right? So this is a data frame from Palmer penguins, and we're going to play with this for our notebook. All right, so any questions? All right, excellent. Okay, then everybody, please go into Posit Cloud. So go to Posit Cloud, log into your account if you need to. I will put in the Zoom chat window the URL to a Posit Cloud RStudio project. This is the same link I've put into the chat window previously in previous workshops, but please click it again to create, because it has been updated with some notebooks that we'll be running through today. All right, so I'm going to click on that link myself here, and you should remember that the first thing you should do after it opens is click the Save a Permanent Copy button. Keep a copy of this project in your RStudio workspace or Posit Cloud workspace. All right, it'll take a second to open. Once it opens, go into the exercises folder. And then once inside the exercises folder, click on our notebook, our markdown notebook called Data Wrangling 01.rmd. And that will open it up in the RStudio source window. And I will pause here and give people a minute to catch up. So again, you're going to posit.cloud, logging in, clicking on the link in the chat window to make a copy of the project, a fresh copy of the project. Click Save a Permanent Copy once it opens up, and then go into the exercises folder and open up the first notebook on data wrangling. And when people get to this point, if you folks could give me a thumbs up in the chat or in your in Zoom, so I can see that this is working. Okay, if anybody is struggling or needs a little more time, feel free to speak up or put a note in the chat window.
Andy, one thing, the cheat sheet, the link to the cheat sheet on website did not work.
All right, thank you, Ben.
Yeah.
Both of them or one of them?
At least the base are.
Okay.
Yeah.
Thank you for that. I will fix those. Okay, let's proceed then. So we are working in a notebook here, and when we run code, which we will soon, the output of the code will appear in the notebook, not in the console. I'm going to keep that default behavior. Therefore, I'm going to minimize my console. We don't really need it for a notebook. All right. The other thing I could say is that notebooks have, you might notice in the toolbar, there's a visual and a source mode, source view. So we're looking at this notebook in source view. You can open it in visual view as well. I'm gonna stick with source view for today. But looking at it in visual is like what you see is what you get, right? But it's still a notebook and it still basically does the same thing. And let me make my screen just a little bit bigger. The eyes.
And
okay.
The screen.
So again?
Also, you are sharing the screen. I see only you in the screen.
Are you not seeing my screen? I'm sorry, say that again.
Yes, I'm not seeing your screen. I'm seeing you.
All right. So
I
I
can
am
see your
screen
screen.
sharing. So
Yeah.
maybe, does anybody else have a problem seeing the screen share? So Esther, maybe
I fixed it. Yeah, sorry.
you found it? Okay. Yeah, you can minimize me. I'm not necessary like that. Yes. Okay. So in the first part of our notebook, we're going to import some messy Excel data. And if any of you are with A&R, and I know many of you are, and if you've worked with the A&R survey tool, when you download data from the survey tool, you get an Excel file. That's the only option there. And like many survey tools, the first, the names of the columns are the verbatim text of the questions, which is not ideal for data analysis. And on top of that, there's two other rows at the top of the spreadsheet that you can't tell it not to give you that don't contain data, that contain other stuff. So these are some of the challenges with survey data. Let's go ahead and handle these when we import it. So go down to code chunk number 1. So scroll down to line 22, click inside there, and then click the little green button to run all of the lines of code in that code chunk. You can also do Control-Shift-Enter if you're on Windows, or Command-Shift-Enter if you're on Mac. And basically, we are getting ready to import this Excel file, which is just simply downloaded from Survey Tool. And file.exists tells us that this file exists. This is just preparation to make sure we type the name in correctly and that there's actually a file at that location. Next, come down to code chunk number 2. And again, run all of code chunk number 2. And then we'll talk through what's going on here. So in code chunk number 2, we are importing this Excel file. And we are using the read Excel package, which is well equipped for reading Excel files. And we're using the read_XLSX function from that package. And you can see the arguments that we are using in read XLS. And I won't talk through all of these. There are other arguments that we could have added, but you can, we're skipping those rows that we don't need. We're actually manually providing the column names. We're not going to use the verbatim text of the survey questions as the column names. So we're using the column names arguments to specify that. We're telling it what types of data. All of this was written manually, right? So I had to look at the spreadsheet. I say column 1 is user. Let's call that user. Column 2 is date. Let's call that registration date. So this all had to be typed in manually. So it's not the easiest thing to do if you only have to do it once. But if you're going to be doing this a lot, this is more efficient to do it. And when all is said and done, we have a nice tibble, and then that we can start using this tibble for whatever we need to do next. And just kind of a little side note here, the names in this fake workshop or event registration survey were created from an R package. There's an R package that will generate fake names, and you can tell it what gender, you can tell it what ethnic group, it's kind of cool. I forget the name of the package, but I could look it up. So that's a little show and tell example of using the read Excel file to ease some of your pain importing Excel documents. All right. The read R package likewise is really good for text data files. We won't do an example of that, but take home message is data wrangling starts when you import. That's what I'm trying to convey here. Any questions?
I have a quick question regarding the equal sign and the difference between the equal sign and the arrow.
Good question.
When would you use either or, particularly for chunk number 2?
Yes, a very good question. So here, the single equal sign is being used as the assignment operator. So the results of read XLS are being saved to an object called reglist tibble. And we're using the single equal sign for that. We could equally use the arrow operator for that. Those are
Gotcha. So it's interchangeable, you could say.
those
Or-
are they're interchangeable if you're using the single equal sign for the purposes of assigning the value to a new object.
Okay, gotcha. Thank you.
Oh, I will say in this particular case, and correct me if I'm wrong, Andy, when there are arguments within a function, it's not the same. You do have to use the equal sign.
Exactly. Yeah.
So you could exchange the first equal sign here for an arrow because you're saving a variable or an object.
yes.
But when you're in this parenthetical scenario, you know, where it says path equals, sheet equals, you're defining arguments instead of objects. And there you have to use an equal sign. It takes a little getting used to.
That makes sense. Yeah, I've seen it as I've seen it where you use it after you're assigning the object, but I never seen it to assign the object, if that makes sense.
Mm-hmm.
Yeah.
Yes, and one of the reasons most people prefer the arrow operator for assignment is because, yeah, in this case, as Genoa noted, when we're passing values to argument names within the function, where the equal sign is playing a different role there, the single equal sign, and just to keep it a little bit clearer, many people will use the arrow operator primarily for the assignment when they're coming to assign, and then use the equal sign for passing values into arguments, and a few other cases. That's mostly it. I've been using the single equal sign in the workshop. Maybe this would be a good time to transition to the arrow operator, because we are using a lot of these. We're using functions and arguments quite a lot from here on out.
It helps me sort my thoughts a little bit. And I know if I'm using an arrow operator, it's going into that global environment in the top right. It's going to be saved. So I can call it again.
Good point. Good point. All right, I'm going to make a note of that. So we will start. All right, thank you. Those are good conversation and good attention to detail. I appreciate that. Okay, let's continue then. So let's now use some of the dplyr functions. And so in code chunk number 3, we load dplyr. It's already been installed in this RStudio Posit Cloud project. It's giving us a couple warning messages that are referring to duplicate function names with other packages. We'll ignore that for right now. But that's just, it shows you, it is an issue. But in code chunk number 4, we're going to specify our package preferences for filter, count, select, and arrange, because those are the functions from dplyr. So go ahead and run code chunk number 4, click inside it, Control-Shift-Enter, or click that little arrow button. And from here on out, we don't have to worry about specifying or telling R which package to use when it encounters the filter, count, select, or arrange functions. Code chunk number 5. Go ahead and run code chunk number 5. We are looking at the Penguins data frame. This is a data set that is bundled with the Palmer Penguins package. That is the primary reason for this package. It's a research data set about penguin measurements. It's got a whole web page and kind of a little following, and you can read about it. It's designed for training, actually. You might notice immediately, oh, there's some missing values there, because in real research data, you have to deal with missing values. So it's different measurements for 3 species of penguins on an island somewhere. Code chunk number 6. Instead of using the head function, we're using the glimpse function. This is another function that you can use to kind of peek into a tibble. It kind of shows you, again, the first few rows of data, but in a different format. Right, I like the glimpse function. I use that a lot. Okay, so code chunk number 7. Go ahead and come down to code chunk number 7. Here, we're going to first pick out just a few of the columns because we don't need all of these columns. So run code chunk number 7. We're loading dplyr again. That's actually unnecessary because it's already loaded. But then we're taking the penguins tibble, piping it into select. So it comes into select as the first argument of select. And yeah, we're not writing that. And then we're providing the names of the columns that we want to keep. And then we're piping that into the head function just to see what that, and note, we're not saving this to a new variable. We're just looking at them. Something else to note here, the names of the columns are not in quotes. That's one of the nice things about most of the dplyr and the tidyverse packages is that you don't need to put column names in quotes. A little bit less typing.
Question.
Yes.
So now with this chunk 7, we are using this piping operator. So first we tell it, okay, take this penguin table, put it through this function that is called select, that selects only some columns, and then let me look at the first 6 rows.
Exactly.
But I guess the question is, from now on that penguins table now only has those 3 columns that we selected, or it remained untouched?
I love this. That is a perfect question. The short answer is penguins, we're not changing the value of penguins. We're simply pulling out these columns and pulling out the first 6 rows and printing it to the console, or in this case to below the code chunk. Because we're not, if we did something like this, if I said penguins and then if I use the arrow operator, this would change penguins, right? If the results of our operation, if we save it back into penguins, then that would change the penguins data frame. Most of the time, you probably don't want to do that. More likely, we would do something like, I could do, say, maybe 3 calls or something. More likely, if you do want to save the results of a dplyr expression, oftentimes you actually save it as a new object so that you leave the original one alone.
Thank you.
Yeah, good observations. Okay, so that's code chunk number 7. Yes, please keep chiming in with these great questions. In code chunk number 8, we're doing something pretty similar here, but we're inside the argument for select, we're simultaneously renaming some of the columns that were selected. So that's something you can do with the select function. You can, at the same time, you can rename the columns using this kind of syntax. All right, so code chunk number 8. Just again, we're just exploring what you can do with these functions. There is another function called rename that would do the same thing, but you can kind of combine both of those things in the select function if you need to do both of those things. Okay, code chunk number 9, go ahead and run that. And let's look closely at what's going on here in code chunk number 9. First note, we're not splitting it across rows. That was my choice when I wrote it. So, you don't have to split across rows. But basically, we're taking the penguins data frame, the pull function from dplyr pulls out a single column and returns it as a vector, right? So it's no longer data frame. The pull function does not return a data frame. It returns a column, a vector of values from a single column. And then we're piping that into table. And you might remember table is from base R, and it generates a frequency table of the unique values. All right. So that's a quick and easy expression to get a quick look at the unique values in the species column. All right, so pulling out rows, easy peasy. Let's look at code chunk number 10, because here we're going to add a new column, and that's that's pretty common in working with data. So I'm going to run all of code chunk number 10, And then let's look closely. How are we creating this new column? You can see it there at the end. It's the bill flip ratio. So we're using the mutate function. And basically the mutate function in the parentheses, you put an expression which defines the values of the new column as well as the name. So the syntax for the expression should be the name equals to, and then some kind of expression that defines the new values. This expression, we're using column names. So it's going to grab the values of every row from those columns. You don't have to, though. We could say bill flip ratio equals 0.5, and it would fill that column for 0.5 for all of the rows, right? So you can use constants or numbers. You can do all kinds of stuff as how you create the new values, including using the values of other columns. All right. So that's pretty handy. And it's a nice, clean expression. It's easy to read, easy to write, and does what we expect. And again, we're not, in this one, we are saving the results of that to a brand new tibble. Okay, so that's how you create new columns, that mutate function. Okay, so mutate in code chunk number 11, we're seeing a different usage of mutate where we're not creating a new column, but we're redefining the values of an existing column. So that's something else you can do with mutate. And here in code chunk 11, if you run that, we're simply that column that we just created, bill flip ratio, we're rounding it to 2 decimal places. Right? So mutate is your friend if you want to add columns or change the values of columns. If you want to drop columns, you could use the select function. But to add columns, you can use mute. There's also transmute, but that's I don't use that very often. Okay, any questions? All right, let's go ahead and do code challenge number 1. So your job in code chunk 12 is to write an expression and add a column called bill flip sum, which is the sum of the bill and flipper length. And I think those are both in millimeters. So hopefully this is a sensible biometric measurement. I'm not a penguin biologist, but anyway, it's an example of a little exercise. Okay, so go ahead and tackle code challenge number 1, code chunk number 12. Create a column in penguins called bill flip sum, which is the sum of the bill length and the flipper length. And if I was going to do this, I would copy paste what worked above and then modify it.
And I just have one quick comment, if that's okay, Andy.
Please.
For those of you who are like me and your brain can't retain every function at every time, if you, and I think we've talked about this briefly, but if you put a question mark and then the name of the function you're trying to use in the console, it will pull up the information about what that function is and what arguments it takes, which is really handy. So
Absolutely.
I also have a quick clarifying question. Are we adding this new column to the tibble or to the actual, to penguins? Like penguin, bill flip, tibble, or penguins?
Yeah, it's your choice whether you save the results of the expression that you type in code check number 12. If you save it to a new object, or just create it and let it, see the results of the console.
Okay.
Or you modify the existing one, but. If anyone gets stuck or it's just like doesn't even know where to start, feel free to unmute and ask a question. Feel free to just watch. We can also help if you want to share your screen. We can talk you through some challenges.
Question.
Yes.
When I click that little green arrow inside the code chunk, does
Yes.
it run the whole chunk or only the line where I'm at with the cursor?
That little green arrow will run the entire code chunk. If you want to run a single line of code, you can use Control Enter, or you can use the run button a little higher up in the toolbar.
Okay.
If you do want to run your lines of code one by one, you can use that run button at the top or just Control Enter.
Thank you.
This is a difference with Jupyter Notebook. Jupyter Notebooks, it's phenomenally hard to run lines of code in cells. What Jupyter Notebooks calls these cells, to run individual lines. I think it's like this all plugin or something. Maybe I'm just not doing it right. All right, does anybody want to share their answer to code chunk 12? Feel free to throw it in the chat window, but not Danielle. It's somebody else. Oh, I like this. All right, thank you, Jared. This looks fantastic. All right, I'm going to run Jerry's code here, and we'll take a look at it. Okay, so I'm going to run Jerry's code line by line, right? So I've highlighted here. I hit Control Enter. Oops. Oh, sorry, I got two people's code here. All right, they both look great. Yeah, that was good. Yes, so as we've seen here, yeah, so the mutate function, yeah, just basically use the same syntax as we saw before to define a new column, which is that adds together the bill length column and the flipper length column, and you can verify that looks good by using the head function or the glimpse function. All right, any questions? Okay, let's keep going. Yeah, we're getting there. So we looked at different ways to manipulate columns. Next, let's look at different ways to manipulate the rows, to sort them, to filter them, and so on and so forth. So in code chunk number 13 in our notebook, go ahead and click down there and then run it, and then we'll see what's going on here. But basically, we are using the arrange function, which is the function you use to sort the rows of a data frame by a column. I should say a column or columns, because if you do want to sort the rows of a tibble by multiple columns, you can, inside the arrange function as the arguments, you can put comma and then add additional column names, and then it'll sort them by the first column, and then where there's a tie, it sorts them by the next column, and so on and so forth. Okay, so arrange is your friend for sorting columns or sorting data frames. In code chunk number 14, go ahead and run that. This is where we are sorting the data frame rows by that same column, but in descending order. And the way you do that is by wrapping the column name in DESC, which to me is not super intuitive, but once you get used to doing that, it's not hard to remember. I will note though, your go-to, you might think, well, I want to sort the rows. Let me try sort. There is a function called sort. It's a function from base R. It will not work in this context. Sort will sort a vector of values and return a sorted copy of that vector. So don't use sort if you're working with data frames. Use arrange, unless you're using base R syntax with the square brackets. Okay, sorting columns is easy peasy. And sometimes if you're looking for like the top 5 values, you just sort them and then pick out the top 5 values. Let's also talk about the subsetting rows. This is also common. And there's 2 functions from dplyr that you could use for sorting, subsetting rows, slice and filter. Most people use filter most of the time. The nice thing about the filter function is that you put in an expression, and the expression can use names of the columns, and you can use Boolean or logical operators like less than, greater than, equal to, and so on and so forth. You can put in multiple expressions inside filter if you want a composite logical comparison, and so on and so forth. So filter is a good one that you can do. Lots of stuff you can do with filter. I'll talk about slice in a minute, but let's look at filter in code chunk number 15. Come down to code chunk number 15, and here we're using filter to only return the rows of penguins where the value in the species column is equal to gen 2. All right, and if we look at the results of that, indeed, we are only getting 124 rows, and those rows only have are only for the gen 2 species. All right. In code chunk number 16, click on that next and run it. Here you can see inside the filter function, there's a double expression separated by commas. And when you provide a double expression inside filter, it will only return the rows where both of those expressions are true. So now we're getting rows where the species equals the gen 2 and the flipper length is greater than 220. And again, if we glimpse the results, there's only 35 columns that meet both of those criteria. And if we look at them, we can see that that's quite true. I will say that if you need a more complex condition expression, such as species equals gen 2 and flipper length equal, greater than 220, or species equals something else, you can do all of that, but you have to write a more complex expression inside. So if you want to use or operators, or more complicated, maybe with with parentheses or combinations of ands and ors, you can do that with the filter function, but you just have to write a custom expression that pulls out the conditions that you want. Okay, so that's filter. Yes, questions? Okay, let's look at code chunk number 17, where we're going to use the slice function. So slice is the other function that you can use to subset rows. And instead of a expression that returns logical values, what the slice function expects are going to be integers for the row numbers that you want to return. 1:5, for example, is the first 5 rows. So in code, yes, question? In code chunk number 17, we're sorting the rows by the bill flip ratio column in descending order, and then we're slicing off the first 5 rows to give us the first top 5 observations in that. All right, so that's one way that you could get the top 5 observation, or the top n values or rows by column. The other way you could do that is using the top n function. So in code chunk number 18, we're using top n. That's another function from dplyr. And if you haven't used dplyr much, you might not know that there's a function called top n. So again, that's where that cheat sheet comes in handy. You can find little functions like that, where basically it's returning the top, in this case, 5 rows, based on the values in the bill flip ratio. And then we're reporting those. So if you run code chunk 18, you should get the same results as code chunk 17. Okay, so we've looked at filter, we've looked at arrange, and we've looked at top n. These are all functions that sort or filter the rows. Any questions? All right. Just for the sake of time, I'm going to let you do challenge number 2 and challenge number 3 on your own. Let's finish up by looking at missing values. Okay. Because a lot of times you do have to filter rows based on missing values. And the way we'll do that is using if you look at code chunk number 21, we're using the filter function again. But if you look at the expression inside the filter function, we're using is.na. We're actually using exclamation point is.na. Is.na returns true, false if the value is missing. And again, NA is how R tags missing values. It's not a mistake, it's just a missing. And the exclamation point flips the falses into trues and the trues to falses. So the exclamation point operator is the negation operator. And again, it works on logical values and it flip-flops trues and falses. So by doing is.na flipper length, is.na body mass, is.na sex, if there's a missing value in any one of those columns, that it'll get thrown out of the results. Okay. All right, let's pause there and we'll come back. And before we look at table summaries, we will look at some more slides. So let's take a 5-minute break and resume at 11:25. Apologies that we went a little longer than the halfway point. We'll take a 6-minute break and see everyone back here at 11:25. Okay, but let's keep going here. So that's a lot of kind of like the manipulations that you'll probably have to do working with data. Let's talk about other common operations when, again, you're preparing data to feed it into a regression, a statistical test, or something else. Oftentimes, you might have tables that you need to join together. If it's a well-structured data set, then repeated values might have been split out into their own table, like a lookup table or something like that. So that's easy. It's easy to join tabular data with dplyr using one of their join functions. So here's an illustration of that. IRIS is a table that comes with R. It has a species column. And then here we have a fake table with some sort of physiology measurements for different species of iris flowers. And it's saved as a separate table, right? So this is table X, for example. This is table Y. And they have a column in common, meaning the values match. This is pretty normal. And you can join. And when we say join, what it means is that the tables themselves aren't getting modified, but what gets returned by one of these join functions will be a new data frame that has the columns together, right? That has all of the columns together in a single table. Left join basically will take, let's look at left join. This is the one you use quite a bit. And X and Y, the first two arguments of left join, should be the two tables, right? And then the by argument, which is where you specify the column or the columns that you want to use to match the rows together. Okay, so X and Y are data frames. That's required. You can't join tables if you don't have two tables. And we'll talk a little bit more about the by column. Okay, if there's only one column in common and it's named the same in both of the tables, you can omit the by argument and the join function will figure it out. So that's just a FYI. And we'll see an example of that. So here we have an example of this. We're creating a fake data frame. I don't know if you've seen before how to create a data frame from scratch in code, but this is what it looks like. Remember, data frames are just a collection of vectors. Every column is a vector. So to make a data frame, you just have to specify expressions that will create these columns on the fly. Okay, so now we have a table or a data frame called iris genetics, and it has a species column there, and the values of the species columns can be used to match to the bigger iris data frame, and we can do that using the left join function. And if you do want to use the by function, then you pass it the name of a column in quotes, right? The column that they have in common. All right, and here's an example of that. So once we've done that, and we'll just pull out the first 10 rows, you can see the new columns from the genetics table are together with the other columns of the iris table, which are the experimental measurements. So that's the essence of it. There are some varieties of that. If the tables should be matched, or if the rows of the table should be matched by multiple columns, you can provide multiple values for that by argument as a character vector. If the name of the column is different, so here's an example of that. You could change the name of the column in one of the tables and then join them so that they match. You can use the rename function from dplyr to rename a column, or you can tweak the way you use the by argument of left join, and you pass it what's called a named vector. Basically, just follow the syntax here, use that combine function, and the name of the vector that you're creating should be the name in the Y table, and how that should be matched to the name in the X table. I think that's right. All right. So in other words, if the names of the columns don't match, it's not a deal breaker. You can either do this trick, or you can rename one of the columns and then join them. Okay. So joining tables, easy peasy. If you do have more tricky joins, like so left join will give you back all of the rows from X and all of the rows from Y that match, and where there is no match, it makes it NA. So for example, if it doesn't find a matching value or matching row in Y, you'll still get that row from X, but the values of the Y columns will be NA. If you want the opposite, you can do right join. There's also inner join, where only where you have matches on both tables do you get back. If you don't have a match, it's excluded. There's an anti-join. There's a few varieties of join to handle all the cases you can probably imagine. And if you have any troubles with this or your headache, feel free to reach out to me or my team. We have a relational database background, so we think in these terms. Okay, what if you need to combine the rows of two data frames together? You've got a folder full of CSV files and you got to combine them. You can use bind rows. And again, the column should be in the same order and have the same kind of data. You probably won't give you an error message if the columns have the same names and the same kind of data, but the results you get back won't be pretty. I'll just say that. All right, so but binding, appending, or merging data frames together is easy. Let's talk about reshaping data, right? So this is going from long to wide and vice versa. This is where you have lots of rows and you want to turn some of those into extra columns, or you have lots and lots of columns, maybe with a lot of NA values there in those columns, and you want to make it long. So this is called reshaping data. That's the general term for this. And the package that you use to do this kind of work, it's not dplyr, but it's dplyr's cousin, tidyr. And tidyr has lots and lots of functions to do this kind of stuff, amongst other. I use it mostly for reshaping data, but you can take a column and split it based into multiple columns. It has other functions for handling missing values and stuff. Oops, I accidentally opened the cheat sheet. All right, we don't have time to go in there, but dplyr is a really handy package, or tidyr is a handy package. But to do that basic reshaping, pivot longer and pivot wider. So pivot functions, which you may have seen in pivot tables from Excel. Pivot's the general verb for reshaping. And these are really powerful functions and can handle all kinds of cases. There's lots of arguments. Sometimes you have to look up a tutorial to figure out exactly how to get them to work. But this is where you would start to reshape your data. Again, from tidyr. Finally, another common operation when you're doing kind of like basic data summarization. This could be called analysis. You might think of this as analysis, but is grouping and summarizing your table, grouping and summarizing the rows of your tables. So group by is the function that you can put into your expression that will take rows and group them together. It kind of does this invisibly. What you get back from group by, it doesn't look like anything's changed, but invisibly, it's noted, okay, these 3 rows are part of the same group. These rows are part of the same group. So group by itself isn't that useful, but almost always after group by, you then take that and you feed it into another function that will compute summaries for those groups of rows. The general one is summarize, and so this is a little bit like mutate. Summarize will generate for every group of rows a new column that contains a summary of those rows in that group. And these are some of the functions that you probably could use in your summarize expression. N will return the number of rows. If it's a numeric column, you can compute the mean, median, sum. If it's a character value, you could use first, and so on and so forth. There's a lot of functions you could use. These are all aggregate functions, right? You give it a number of values and it spits out a single value for that group. Okay, so let's look at a little example of group by, and then we'll see some more in the exercise. But again, that storms tibble from the dplyr package. So we've seen this before, but we'll just see it again. We did notice, though, that there is, for a single day, there's probably 4 measurements, 4 records in this table. So depending what you're doing, you might not be interested in the hourly by hour wind speed, but maybe just the average wind speed for that day. So this is a tibble that's kind of ripe for grouping the rows into groups, say by day. So let's take a look at that in this example. Here we're actually going to group the records by month, and then we're going to, for every month, we're going to count up the number of observations, not the number of storms, because again, there's 1 to 4 records per storm, so we're not quite doing that. We'd have to group by the name, and then throw out the extra records. But here's how you do it. So again, group by. If we stopped here, we would get back what looks almost identical to storms. Invisibly, the rows would be grouped, but that's not helpful unless you follow it up by summarize. And again, inside the expression for summarize, we're defining a new column for every group, in this case, every month. And we're using the n function, which returns the number of rows in that group. All right, so that's an example of how you use group and summarize. And just as FYI, if you're interested in working with spatial data, the spatial data frame, using the SF package, when you do this group and summarize on spatial data frames, it also gives you back, it takes the geometry of those features and unions them by group, which is really cool. That's what you would do, the counterpart of the summarize operation in the ArcGIS world. But that's a digression. Okay, let's go into, let me pause for a second here. So we looked at working with grouping, and we looked at reshaping data, and we looked at joins. We're going to do that next. All right. Okay, let's go into Posit Cloud, please. So go back into Posit Cloud, into our workshop project. Wake it up if necessary. And we're going to abandon Data Wrangling 01 and go to Data Wrangling 02. So go to the Files pane, go into the Exercises folder, click on Data Wrangling 02, and this will open up a new notebook. And we will go through it here. Anyone's having challenges, please speak up. If not, I'll assume people are keeping up or watching at this point, which is fine as well. In the spirit of reproducibility, this is a new notebook, so I'm going to restart my R session. So I'm going to go to the session menu and click Restart R. This is optional, but good practice when you're working with data analysis to start fresh. So after I've done that, I restarted my R session. It didn't clear out my environment panes. I'm going to use that little broom button and get rid of all those objects in memory. Okay, on to notebook number 2, where we're going to do some of this joining and summarizing and reshaping data. So code chunk number 1 in our notebook. Go ahead and click in there and run the whole thing. This should look familiar. We're loading the dplyr package and then specifying our package preferences for the functions in this package. Okay, so let's create some summaries of data. So code chunk number 2, the first thing we're going to do in code chunk number 2, again, we're working with the Penguins data frame, is we're going to use that summarize function. But note here in code chunk number 2, we're not doing any grouping, right? So because we're not doing any grouping of the rows, the summarize function will compute summaries of all of the rows, right? So we could kind of do this with mutate as well, but mutate is row by row. So if you want to take summaries of groups of rows or the entire table, then use summarize. I'll go ahead and run all of code chunk number 2. And here we are computing the mean of the bill length, bill depth, and body mass. A couple things to note here. This might be silly to do because there's 3 species of penguins, so you wouldn't expect them to have, but you can compute means. But note also that the mean function that we're using for the values of these columns includes the na.rm optional argument, because we know this table does have missing values in some of the columns, and we don't provide na.rm, which means remove those na values, then we're going to get na means, because the default function of the mean function is to return na if any of the values are missing. That's code chunk number 2. So we've computed the mean of those 3 columns, and we're getting back a table with those means. Code chunk number 3, go ahead and run code chunk number 3, click in it, and then run the whole thing. This is basically a copy paste of code chunk number 2, but notice now we've inserted a group by statement before we do summarize, and that invisibly groups the rows in the data frame by the unique values of species, and then it uses those groups of rows when it computes computes the means using the summarize function. So now we're getting back something which is probably more useful in an analysis. We're getting the average per species of those 3 body measurements. All right, any questions?
I do have a quick question. When you remove the NAs and you calculate the mean, it just calculates the mean for the actual values, not the missing values as well. Is that right?
Well, if you take out na.rm, let's go ahead and do that. See what happens. Na.rm, it is not a required argument because it has a default value and the default value is false. So if I run it without na.rm, you can see not all, but many of the means of per species are na, because it means there's one or more records of, say, Gen 2 penguins where there is no bill length measured. They forgot it or something happened. So so the mean function is returning NA as the mean because we haven't specified that, it's making a safe choice on your behalf to report the mean as missing if any of the values are missing.
Yeah. One of the ways I like to check before I organize my data, whether or not they're NAs and anything else that I might be concerned about, is just to type in summary and then the name of the data set, and it will print out I think the first quartile, mean, median, and how many NAs are in each column for the whole data set.
Oh, I love that. I'm gonna
Maybe
run
it's a tidyverse function, but if it's dplyr, it should work. There you go.
Yes. Oh, I love that. Thank you, Genoa. So summary, we have seen this before. It's a general purpose function. And if you give it a data frame or a tibble, you'll get a little summary picture of each of the columns. If it's a character column, we get a frequency table of the unique values. If it's a numeric column, we see the quartiles, but then what Genoa's highlighted is that the summary of each column also tells you if there are any NA values there. So
it's also a really great way to find out if they had an NA value that's a number in the data set that's like 2 million. Because sometimes with especially rasters, they have this absurd number for values that are NAs because they can't have text as an argument in the data. So if the max is something completely unbelievable, you might want to think about that being a filler value to filter out.
Yes, it could be a filler value. It could be like a negative number or whoever created the data, this is the kind of stuff. If you're lucky enough and you have the patience to read the metadata, and if they actually provided metadata, you might see that kind of stuff. But otherwise, you can kind of guess and then make. And the summary function is a good one to do that. Excellent. Okay, let's keep going. We've got 10 minutes to go here. So in code chunk number 4, we're doing a similar kind of operation: group by followed by summarize. And here we're simply computing for each island. I guess there's 3 islands, I think. For each island where these measurements come from, how many records per island, right? So again, we're using that n function that returns the number of records in that group. So it's pretty straightforward. Okay. So code chunk number 5 is a challenge question. Let's pause here. And your job is to compute the number of observations per year. So I believe there is a year column, and you do know how to use group by and summarize together to count up the number of records per group. So go ahead and tackle challenge number 4, code chunk number 5. Hopefully this will be quick. Feel free to also do challenge number 5 below the next one, where you're being asked to compute the number of observations per year and species. Well, that's kind of interesting. So for every unique combination of year and species, how many observations were there? We have not seen an example where we're grouping by 2 columns. So see if you can figure that out. All right, let's proceed here. So compute the number of observations per year. Well, let's start with penguin. That's probably a good place to start. And I'm going to pipe that for, I kind of forget the names of the columns here. So I'm going to use that $ operator. Let's see. We're looking for, is there one called year? There's one called year. All right. Well, this would be pretty easy. All right. So I'm going to pipe that into the group by, and we'll do the group by year. You don't have to put the name of the column in quotes. And then summarize is the name is summarize. You can use, if you're, whether you prefer British or American spellings, you can use either version of for the summarize with the S or the Z. And then we'll say num observations equals to n. Let's see if this will work. All right, that seemed to work. All right, and then for chunk number 6, or challenge number, code chunk number 6, challenge number 5, here we're asked to compute the number of observations per year and species. There's a couple ways you might be able to do this. You might be able to like group them by year, and then actually no, you need to group. There's only one way to do this. You need to in your group by function, you need to specify 2 columns, and it's going to be you simply provide the second column or subsequent columns as additional arguments to the group by function. And if I run this, now we can see we're getting the results are not, it's not a 2-column tibble, it's a 3-column tibble. And we can see for every year, there's a row for every combo of year and species. All right. And yeah, so that's how you can group on multiple columns. And this is a nice tidy format if we wanted to plot these and maybe make them as separate dots or separate series. We could work with this, but we'll see in a bit how we could reshape that too if we wanted those years to be separate columns. Okay, let's proceed. Code chunk number 7 here. What we're going to do is we're going to practice using joining tables together. So code chunk number 7, we are loading up a CSV file using read_CSV. We haven't seen read_CSV. We've seen read.csv. Read_CSV is from the readr package. Not really critical here. We could have done r.csv. This is a well-structured CSV file. But as you can see, it's some more fake data for penguin species. Code chunk number 8, we're loading the Palmer penguins package again for about the 10th time in this notebook. That was not necessary. It doesn't hurt. But then we're using left join. So we're taking penguins, we're piping it into F join, so it pops into left join as the first argument, which is the first table. And then the second argument of left join is the genetics table. And here we are manually telling it that the column that they have in column is called species, all lowercase. That's probably optional in this case because I suspect that's the only column they have in column. Unfortunately, it's spelled the same. All right. But now that we've done that, if you scroll over to the right, you can actually see those new variables for each species. All right. So that's a join. If your columns are actually do indeed have matching values, it's pretty painless. If they don't have matching values, you may have to do some resampling using mutate, for example, to make them match. Okay, next, code chunk number 9. This is where we're going to do that long to wide kind of thing. So if you run code chunk number 9, we are importing a CSV file which contains climate data, projected climate data. This came out of R package I wrote called CalAdapt R. If you're curious about this, it queries the CalAdapt server. So what we're getting though here is daily projected temperature data for Sacramento, both minimum and maximum projected daily temperature for probably 3 probably 4 climate models. I don't know how many mission scenarios, but this is an example of a CSV. It's got a lot of data, right? So one thing you might want to do is, because the rows represent either minimum or maximum temperature, that's what that first ClimVar column contains, Tasmin or Tasmax. You might want to split that out into separate columns. So that's what we're doing in code chunk number 10. Using pivot wider, we're telling it get the names of these new columns it's going to create from that ClimVar column. So that's normally a character value, and then grab the fill those columns with the temp F column. So that's what the values from argument does. And now that we have the minimum temperature as a separate column, the maximum temperature as a separate column, in code chunk 11, we can simply go back to mutate, simply subtract them to get the range of temperatures for every day, again, for projected in 2050 into the future, right? So that's a quick example of reshaping data, an example of why that could be useful. All right, let's end there. We're right at time, but we covered a fair bit. We will come back to some of these processes next week, because the focus of next week is plotting, but to get data in shape to make a plot, oftentimes we're going to have to come back to some of these functions. So hope to see most of you back for that one.